Hello, my name is Rybicki. In this talk, I will present our recent work on weight-free approximate agreement on graphs. This is joint work with Jan Alister and Faith Ellen. Consider a distributed system that consists of n processes. Many fundamental tasks in distributed systems take roughly the following form. Each process I is given some input value xi, and the process should generate an output value yi, which is somehow constrained by the input values given to all the processes. These output values can represent, for example, a collective coordinated decision. Perhaps the simplest distributed agreement task is the consensus problem, where the constraint is that the output of all processes should be exactly the same, and this value has to be an input value given to some process I. However, it is well known that consensus tends to be either very hard or even impossible to solve, depending on the model. As consensus is hard, many relaxations of consensus have been studied in the past. One class of such problems are approximate agreement tasks. Instead of trying to reach perfect agreement, the goal is to agree on output values that are sufficiently close to each other in some sense. The simplest variant of approximate agreement is the following. We treat every input value as a numerical value and require that all output values generated are within distance epsilon from each other, where epsilon is a given fixed constant. Moreover, we require that the output values resides between the interval ranging from the smallest input value to the largest input value. It turns out that this relaxation is in fact much easier to solve than consensus. Now, instead of treating the inputs and outputs as numbers, we can also consider a more combinatorial version of the problem. We can discretize this problem by assuming that the inputs and outputs are actually vertices of some given graph G. Now the input of process I is a vertex xi in the graph G. As before, there are two constraints, but we phrase them slightly differently now. First constraint, known as the validity condition, says that the output values must reside on the shortest path between two input values. The second constraint is the agreement condition, which says that all output values should be within distance 1 of one another. Note that if we require that the distance is to be less than 1, then this actually amounts to solving consensus, which is hard. When the graph G is a tree, the problem is fairly easy to solve. However, when we move on to graphs that also contain cycles, the problem becomes much more interesting. Indeed, sometimes the problem is provably hard to solve, as we will soon see. Note that regardless of the given graph G, the problem definition always remains the same. The output values should lie on the shortest path between two input values, and the output values should be within distance 1 of one another. That is, the output values form a clique. The question we investigate in this paper is as follows. On which graphs is approximate agreement easy to solve? To address this question, we consider the following model of computation. We operate in the standard asynchronous shared memory setting, where an adversary controls when and in which order processes perform their computational steps. The processes communicate by writing values to and reading values from the shared memory. We focus on algorithms that tolerate highly asynchronous environments. An algorithm is said to be k-resilient if an adversarial scheduler can crash at most k processes in the system, and regardless of this, all the non-crashed processes still eventually terminate with correct outputs. A weight-free algorithm is simply a n-1 resilient algorithm. Before discussing some technical results, let's briefly overview what is already known about approximate agreement on graphs. The case of paths has been well understood for a long time now, both in the asynchronous shared memory setting and in the message passing setting. In fact, in the message passing setting, it is possible to tolerate arbitrary Byzantine failures instead of just crash faults. The problem has also been studied in the case of chordal graphs under a slightly weaker validity condition, which requires that the output values reside on some minimal path instead of a shortest path connecting a pair of input vertices. This algorithm was given in the message passing setting, and it tolerates up to n over omega plus 1 faults, where omega is the size of the largest clique in the graph G. Recently, Alcantara and others studied a very similar problem in the context of asynchronous robot gathering. In this gathering problem, the validity constraint is relaxed even further. If the input values form a clique, then the output values have to be a subset of the input values. In this setting, there is a weight-free algorithm for graphs whose click graph is a tree. This class of graphs is a strict subset of chordal graphs. Finally, Castaneda and others have showed that the gathering problem and its variants cannot be solved in a weight-free manner on cycles of length greater than 3. This result actually generalizes to each of the above problem variants, as all of the 3 validity conditions turn out to be the same in the case of cycles. However, this does not thoroughly answer the question, when can approximate agreement be solved under the shortest path validity constraint? For example, are cycles the only hard case? In this vein, we give some new results. First, it is not hard to see that a one-resilient protocol exists for any connected graph. Thus, while weight-free protocols do not exist for all cycles, one-resilient protocols do in fact exist. Second, we show that for a class of graphs, which we call nicely bridged graphs, the problem can be solved using a weight-free algorithm. This class of graphs is a strict superset of chordal graphs, as these graphs can also contain long-induced cycles. So in a sense, this result says that induced cycles per se are not an issue preventing the existence of weight-free algorithms. On the negative side, we give a new topological proof of the impossibility of weight-free approximate agreement on cycles of length greater than 3. This result uses a generalization of Spörner's lemma to convex polygons. Moreover, we show that in a sense, there is no simple proof of this result. There exists no extension-based proof that shows the impossibility of weight-free approximate agreement even on cycles of length 4. Informally, this means that unlike for consensus, there are no simple valency-based arguments to show the impossibility of weight-free approximate agreement on cycles. Finally, we give a new large class of graphs on which there is no weight-free protocol for approximate agreement. Let's start by examining on which graphs approximate agreement cannot be solved in a weight-free manner. To this end, I want to first present a variant of the clever reduction by Castaneda and others. While they consider a slightly different problem variant, the reduction actually shows that approximate agreement is hard on cycles. We can then easily extend this argument to some other types of graphs as well. The proof is via a reduction from two-set agreement, which is a relaxation of the consensus problem. So let's quickly recap what is the definition of the two-set agreement problem. In two-set agreement, each process is given one of the possible input values from the domain 1, 2, 3. There are two constraints. First, every process should output a value that was given as input. Second, there should be at most two distinct values that were generated as output. These are the validity and agreement conditions of two-set agreement. Despite being a relaxation of consensus, two-set agreement is not in fact that much easier than consensus. There is no weight-free algorithm for at least 3 processes, but there is a one-resilient algorithm for any number of processes. This breakthrough lower bound result was simultaneously shown by 3 groups. The proofs of this result typically rely on topological arguments. However, for now, let's just assume that this result is given. Using the hardness of two-set agreement, there is a simple proof of the impossibility of weight-free approximate agreement on cycles of length at least 4. The proof I'm going to present now essentially follows the reduction given by Castaneda and others with minor modifications. The idea is to show that if there is a weight-free algorithm that solves approximate agreement on a cycle C, then we can solve two-set agreement in a weight-free manner. However, as we just discussed, this cannot be done if there are at least 3 processes in the system. For the sake of contradiction, let us assume that such an algorithm exists. As the first step, we color the vertices of the cycle C as follows. We take 3 consecutive vertices of the cycle C and color them with red, black, and blue. These colors correspond to the input values 1, 2, and 3 for the two-set agreement problem. The remaining vertices of the cycle C we can just color blue. Now we will solve two-set agreement as follows. In the first step, processes with inputs 1 and 3 start on the red and blue vertices of the cycle C. Then they run a weight-free approximate agreement algorithm for the path obtained by removing the black vertex of the cycle C. Recall that approximate agreement on the path is an easy problem and can be solved in a weight-free manner. Thus, the values of these processes will converge to vertices on some edge of the highlighted path. In the second step, we will use the weight-free approximate agreement algorithm on the cycle. Processes that had input 2 for the 2-set agreement instance will use the black vertex as their input for the cycle agreement protocol. The other processes use the output of the approximate agreement algorithm on the path. By the agreement property of approximate agreement on cycles, the outputs will converge to vertices incident to some edge in the cycle C. In the last step, each process will simply output the color of the vertex output by the cycle agreement protocol. This color is then taken to be the output value for the 2-set agreement problem. Note that since all processes converged on the vertices incident to single edge, there are at most 2 output values for the 2-set agreement problem. So the agreement condition of 2-set agreement is always satisfied. Now, let's think about why validity holds. The output values have to be a subset of the input values. There are 3 cases. First, if there are 3 distinct input values in the 2-set agreement instance, then any output value will be an input value. So this case is easy, since we need to only worry about the agreement condition. For the second case, suppose the inputs are a subset of the set 1, 2 or the set 2, 3. If the inputs are from the set 1, 2, then it is easy to check that validity holds. Every value output will be incident to the edge between the red and the black vertex. The second case, where the inputs are from the set 2, 3, is symmetric. The remaining case is the case when some processes have input 1 and others have input 3. Let's see how this plays out. Suppose the inputs for the 2-set agreement instance consist of value 1 and 3. Now all processes run the approximate agreement on the path obtained by removing the black vertex from the cycle C. Now the input vertices are incident to some edge of the path, and so the cycle agreement algorithm will also output vertices incident to this same edge. Since this path is only colored with colors red and blue, which correspond to the input values 1 and 3, validity is also satisfied. Since the agreement and the validity conditions of 2-set agreement always hold, it follows that we have solved 2-set agreement using a weight-free protocol. Now this argument can be generalized to other graphs as well. So suppose we have a labeling of the graph G with 3 colors, red, black and blue, that satisfies the following 3 properties. First, there exists no triangle with all 3 colors. Second, there exists some cycle C with 3 consecutive vertices with colors red, black and blue. And finally, the color black is used exactly once on the cycle C. Now essentially the same argument shows that approximate agreement will be hard on any graph that admits this type of a labeling. But of course, these labelings do not always exist. For example, for the graph given here, adding a single edge between the center blue node and the black node would prevent the existence of this kind of a labeling. Moreover, graphs that do not contain any cycles at all, of course, cannot have such a labeling. So we have now seen examples of graphs that do not admit weight-free protocols for approximate agreement. But let's now see when we can actually solve approximate agreement on graphs. As a warm-up, we will consider how to solve approximate agreement on any connected graph using a one-resilient algorithm. This algorithm has 2 steps. The first step is to reduce the number of possible input vertices to at most 2 by running a 2-set agreement algorithm as a pre-processing step. This can be done in a one-resilient manner. The second step is to solve approximate agreement under the promise of having only 2 input values. Handling this case is fairly easy and can be done in a weight-free manner. So let's see how to do this. First, we fix for every pair of vertices u and v a single vertex G of U and V that lies in the center of a shortest path between the vertices U and V. Since all processes know the graph G, we can fix these center vertices in advance. The algorithm itself will proceed iteratively. In each iteration K, every process performs the following 3 steps. First, a process writes its current value, which is initially its input vertex, to the shared memory. The value can be either written to a snapshot object, sk, or just simply to some predetermined location in the shared memory. After this, the process scans the memory to obtain a set of vertices written by other processes and itself during iteration k. Note that since the process itself writes a value in the shared memory before reading the shared memory, its scan will return a non-empty set. Also, since we assume that there are at most 2 input values to begin with, the set returned by the scan will have size at most 2. In the last step of the kth iteration, the process will check if the scan returned 2 unique vertices, and if it did, it will move the center of these 2 vertices as given by the map G. In general, since the system is asynchronous, the process will write into the shared memory and read values from the shared memory in some arbitrary order. However, all processes that complete their scans will obtain some non-empty set of vertices of size at most 2. In fact, these sets can be ordered by set inclusion, and there is some vertex U that is returned by the scan of all processes. Now, when the processes apply the rule in the 3rd step, we get that processes whose scan returned the set consisting only of the vertex U will stay in the vertex U. The other processes will set their current value to be the G of U and V, where U and V are the 2 values returned by their scan. Thus, for the next iteration, unless the vertices are already within distance 1, we start with values that are strictly closer than in the previous iteration. So in conclusion, we get that the distance will reduce by roughly of a factor of 2 in each iteration, so eventually the algorithm will converge and we will have solved approximate agreement on the graph G. Now, let's see how to use a similar idea to obtain a weight-free algorithm for nicely bridged graphs, a superclass of chordal graphs. Our approach is to use the same kind of an iterative process as before. However, now we do not operate under the assumption that there are at most 2 distinct input vertices. So we need to find an update rule that takes a set x of vertices onto a single vertex on a path between some pair of vertices in X. This rule should reduce the distance between the proposed values in each iteration to guarantee convergence as before. Now, in order to find such a rule, we need to exploit some properties of the underlying graph. Why? Well, because we know that the problem cannot be solved in a weight-free manner on all graphs. It turns out that for a fairly large class of graphs, the following update rule will work. We choose g of x to be a vertex in the center of the convex hull of X. With this rule, we can use the following relationship between the radius and the diameter of bridged graphs. So for these bridged graphs, we can show that each iteration reduces the diameter of the relevant portion of the graph by roughly 2/3. But I have not yet explained to you what this rule actually means and what are these bridged graphs. So let's discuss that next. So let's start with a definition of the convex hull. The convex hull of a set of vertices X is the set of all vertices on all shortest paths between any 2 vertices in X. So for example, the convex hull of the blue vertices here is the following set, and this would be the graph induced by the convex hull. Now let's define what is the center of a graph. The center of a graph G consists of the set of vertices that minimize the maximum distance to any other node in G. This distance is known as the radius of the graph. We refer to the center of the convex hull of a set X as the center of the subgraph induced by the hull of X. Finally, I need to explain what are these bridged graphs. The class of bridged graphs is a generalization of chordal graphs. Recall that the graph is chordal if it contains no induced cycles of length greater than 3. The graph on the left is chordal, but the graph on the right is not because it contains an induced cycle of length 6. A graph is bridged if it contains no isometric cycles of length greater than 3. Every chordal graph is in fact also a bridged graph. So let's look at the update rule again, now that we know what it means. With this rule, a process always chooses a vertex in the center of the convex hull of the values it observed in a given iteration. Therefore, the algorithm will reduce the diameter of the portion of the graph where the current values reside from d to at most 2/3 times d plus 1. But note that this rule can in fact get stuck when the diameter is 2. This can happen when the radius and diameter are both 2. Such graphs are called two self-centered graphs. In these graphs, the center of the graph consists of all the vertices of the graph. Now, handling this situation seems to be somewhat tricky, as it requires some symmetry breaking among the vertices. However, if all such two self-centered subgraphs of G are chordal, then we know how to guarantee convergence. This is because for chordal subgraphs, there is a way to choose a vertex in the center of this subgraph in a way that will guarantee progress. The details of this final step are given in the full version of the paper. So, in any bridge graph, where every two self-centered subgraph is chordal, we can solve approximate agreement in a weight-free manner. Every chordal graph is such a graph, but there are also graphs in this class that are not chordal. Now, we have a large class of graphs on which approximate agreement can be solved using a weight-free protocol under a stronger validity condition that has been considered before, and another class of graphs on which approximate agreement is provably hard. However, it's not yet clear to us what is the exact graph property that characterizes the weight-free solvability of approximate agreement on graphs. So this remains as an open problem. In the paper, we also extend these results to the message passing setting and give a direct topological proof of the impossibility of weight-free approximate agreement on cycles without going through a reduction from two-set agreement. For more details, I invite you to read our paper in the conference proceedings or take a look at the full version available on arXiv. Thank you for your attention.